Log on, tune in, find out. Another good idea from Cambridge.
Without further ado, it's a great pleasure to have Alessandro here from Milan. It's Milan, right?
Yeah, it is.
Who's going to tell us about He's going to tell us about that stuff. Thank you very much.
Thank you. Thank you for the technical assistance, for the invitation here. So, how does this thing work? I'll start with an introduction without wasting any more time. So let me start from far actually. So one of the motivations for this work was in a line of a long tradition to try to reformulate gravity in terms of forms instead of using symmetric tensors. That's basically because forms are easier to deal with. And well, perhaps the first example that everyone will recognize is just the humble use of field brane instead of using the metric. When you compute the spin connection in terms of field brane, you're using the external algebra instead of having to contract stuff in weird ways. Maybe not that the usual formalism is weird, but that one is often more speedy. And well, that has evolved also in other formalisms, which I will not be commenting on. But maybe a better example is, this is an example of what I mean, but here you're using just one forms. One forms are not really using the, they are forms, they're also vectors, but where you're really using the formalism of exterior algebra in an essential way is, for example, when you, in 4 dimensions, if you try to reformulate gravity in terms of a triplet of forms, as these people did long ago. And, well, I'm not going to tell you how gravity gets, how the action, gets reformulated, but let me just point out that you start from the usual symmetric tensor and you go from something which is antisymmetric. And well, the usual Lagrangian, the Riemann-Hilbert Lagrangian gets translated into some BF type theory. And in, let's say, modern language, I would say that this is, I will review this stuff, but for those who know something already, can say that this is, today we will call it an SU2 structure, this triplet of forms. So, well, many people thought that this was going to help with quantization. Now, I'm not going to do that. This is not my aim. Instead, I'm going to show you that supersymmetry leads you to something very similar, and now your main aim is to use this reformulation to find classical solutions. Then who knows, maybe it might also be useful to reformulate the action of string theory in a certain way, but I will comment on that later on. For now, let me start. Okay, so this is a very schematic depiction of what supersymmetry looks like. So instead of having supersymmetry, is a bit like having an isometry. Instead of having a vector generated symmetry, have a fermion generated symmetry. And well, it's very schematically, for example, so there's a metric. There's also a metric in fermionic direction that we call Gravitino, and then its transformation has schematically this form, very schematically. Then usually we set the fermionic fields to 0, and that sets automatically all the variations of the bosonic fields to 0. Now, if we set also the Ramon-Ramon fluxes to 0 for simplicity, then we get that setting the variation of the other fields, of the fermionic fields, to 0 gives some easy equations. Basically, all you get is that the space should have recitative holonomy. If that happens, then what you have accomplished is that your spacetime has this symmetry, has this extra symmetry, which is not an isometry, but it's called supersymmetry. Now, you might say, okay, I know all about it already. I mean, this audience, certainly many of you know more than I do about this particular set of solutions. But the point I want to make is that even in this very simple situation, finding solution is easiest in terms of forms. What you do is not actually looking for a solution to this equation, but you reformulate it. Let me review very quickly how. So you start by defining bilinears in this way. These gammas are just antisymmetrized products of gamma matrices, and hence, by definition, this is antisymmetric and antisymmetric tensor. Since this is a bilinear, all fermionic indices are saturated, so these indices are the only one that this object has. And, well, this is a form, then. And if we, for example, consider a spacetime of this with this factorization, then we get this equation becomes actually, so let me write m instead of mu for an internal index. And it turns out that this is equivalent to, well, first of all, you build out of this fermion. In this case, you can only build, it turns out, bilinears with 2 legs or 3 legs. So you have a 2 form that I call J and a 3 form that I call omega. And this, from now on, I'll use this very common notation where the derivative, the antisymmetrized derivative, is schematically depicted with this D operator. Now, these differential equations can be just obtained by the definition of J and omega, which are bilinears in the spinors, and this. So these are easy consequences. But also, well, you can find certain algebraic equations that relate these bilinears in the fermions by using essentially Firth identities. Now, so deriving all this is trivial. Less trivial is to show that they are also equivalent to having covariantly constant spinor, but less trivial, but still a few lines. It's not that bad. So basically, these two just tell you that the two form, if you have a 2 form and a 3 form, and these are satisfied, J and omega can be obtained as bilinears of a fermion, and then these 2 equations tell you that that fermion is also covariantly constant. Now, I'm probably insulting your intelligence here, but the point I'm trying to make is that actually it's in this form the Calabi-Yauch were found. It turns out, namely, that the first 3 equations are very easy to solve. Basically, this tells you that the manifold is complex. This tells you then that it's symplectic, or if you want, that it's scalar. This is a compatibility condition which is almost automatically satisfied. If you open a book in algebraic geometry, it teaches you basically how to solve all 3 of them in a few seconds. And then the last one is really the hard one to solve, but that's what Yauch's theorem shows how to solve. In any case, my point is, even in this very simple case, this equation is actually harder to solve than this system, even though this system looks longer. Let's now.
Can I ask a question about that simple system? Somehow, at the end, we know that omega is a holomorphic 3 form, right? So omega is holomorphic and J is 1, 1. So how do those things? It's not immediately obvious.
It's in here.
So those I see. So the first 2 don't tell you.
Well, okay. So yeah. I have slightly cheated in the interest of. So there is one condition that they should say about omega, which says that it's decomposable. Now, if you say that, then it's automatically it will automatically be the 3-0 form for some almost compact structure, then this will tell you that that almost compact structure is actually integrable. And then this will tell you that since omega, I just told you is 3-0, then J has to be 1-1 because of this equation. Because the 2-0, this sets to 0 the 2-0 part of J, but J is real, so also the 0-2 part. Yeah. It's just a reformulation, but it's one that would be closest to what I'll be doing. All right, so now we don't, in general, this was an easy example, but as you might imagine from the way I put things, in general, I'm interested in having Raman fields on. And then what happens is that you get a messy system, which has no clear holonomy interpretation. Even in this particular, if you have this particular factorization, the holonomy route somehow doesn't tell you much. But it turns out there's an alternative way of understanding. So instead of, see what I'm saying is that there's no clear analog of having a covariantly constant spino, because it's not just that you have this equation that has an extra contribution actually. Then here I was also not telling you about the transformation of the Di Latino, which becomes suddenly non-trivial. Then if you restrict to an ansatz like this, you get that they start factorizing, and you get a messy system of 6 equations for 2 spinos actually, not even just one, because it's type 2, there isn't just one spino here. Anyway, it's complicated. So nabla epsilon equals 0 doesn't have a clear and elegant analog, but the other system, the one that used to be here, does. And that's what we found a few years ago. Here's schematically, well, I have suppressed again a couple of details, but basically that's it. You have a reformulation that looks like this, and you might wonder what the phi's are. But first of all, maybe I should also tell you this is in 2b. I've chosen to focus for this talk on 2b. For 2a, the changes are very minimal. For example, in this case, it would just exchange plus and minus. But, well, in both cases, 2a and 2b, this equation has interpretation. Phi plus and phi minus are certain forms that, again, should satisfy certain algebraic constraints. The analog, this would be the analogs of the 2 constraints J where omega equals 0, and the other one that we saw in the previous slide. Right now, I'm not writing them here, but I will review them very shortly. So we would have those. And they tell you in particular that phi plus and phi minus are, let's say, pure spinos. This is the terminology that is usually employed, even though they are not spinos, they are just differential forms. And one of the good things about this reformulation is that, for example, mathematicians had actually studied equations like this. Well, I mean, quite recently, I would say. So they interpret this name, for example, was given in 02, only three years earlier than our paper. And F, finally, just the Raman fields, which are also differential forms of this locally differential forms. And hence they're also antisymmetric. They fit very well into the scheme. Now, similar equations also exist for the case where the factorization has a ADS factor instead of Minkowski factor.
So I just missed a basic point there.
Yeah.
The phi's were spinners.
They're usually called pure spinos. They're actually differential forms which satisfy certain algebraic constraints. The reason they're called pure spinos is that mathematicians like to think of them as spinos for the doubled Clifford algebra, the one Clifford 6-6.
Yes.
So, but the thing is, forms, differential forms, are a representation for this doubled Clifford algebra. That's why they're called spinos. But
I'm just trying to understand how you have an equation here which would be d phi plus is equal to f.
Phi is a form.
But then f would be a particular Raman field.
well, then you have to solve the equation.
No. What I mean is, if
But I guess
if it's a spinner,
it's
then
a
you have to
sum
roll
of
it.
different degrees, right? It's a sum of forms of different degrees.
Yes, phi and phi 2. Yes. Oh, okay.
Oh.
Now, thanks. I hadn't gotten the point of the question.
Then
Thank
phi
you.
is also a sum of different degrees. Or else
So
then
yes,
you-
all of them are sums. I'm sorry, I have been.
Okay, that's fine.
Yeah. So the problem is when you interact too much with mathematicians, and in my case, that happened during my education. So mathematicians usually, what happens is mathematicians usually say, when they say form, they just mean a formal sum. What we would say is a formal sum of forms of different
I see.
degrees. And for them, it's perfectly okay to sum a 0 form and a 2 form.
Yeah,
And I got into this habit.
That's
So whenever I say form, please understand that I mean a formal sum of forms of different degrees. I don't, and that plus and minus just said plus meant even form and minus odd form.
Okay.
Now, as I was saying, that was for Minkowski. This is just for, and now I'm telling you, there's also a version for ADS that was also found shortly afterwards, 2005. And it's important, for example, because it's holographically dual to CFT trees, for example, which have become later important in our field. But, well, what about other spacetimes? So, for example, what if you want to embed a 4-dimensional supersymmetric black hole in 10 dimensions? I mean, we expect that in general this will be doable for black holes that live in n equals to tiers that come from reductions on Calabi-House. We expect that should be possible because those have a brane interpretation. But for more complicated situations, that's not clear, and maybe you want to do it directly in 10 dimensions. At least I do. Or other people more recently came to me asking, all right, I like to have a version of the same formalism that allows you to look for solutions of this type. Because there is the formal appeal of the equations that I showed you before, but there's also the fact that, practically speaking, it allows you to look for supersymmetric solutions. You plug them, you just write down if you want, you can decompose them into their various components of different degrees. You get usually a system of ODEs once you have, for example, set up a certain ansatz with a symmetry. But, yes.
Direct product, you mean semi-direct, so warping is allowed.
Warping is allowed, yes. Yeah. Some people use the semi-direct product here. I would put a W maybe, but yeah, anyway, I actually mean warped. Warping is allowed. That's actually the detail that I surprised in the previous slide. That the warping function would have appeared in a certain way. So, well, all this doesn't enter into this formalism. And also, another thing that doesn't enter into this formalism is factorizations of other types. With Minkowski with another dimension here, or ADS with another dimension. Now, you may not care about Minkowski vector, Minkowski 5, for example, but you do care for ADS 5, presumably, because of holography. And today we also care about these because they are holographically dual to non-relativistic CFTs, and so on.
What about
Sorry?
what about d zeta?
The zeta?
Yes, yeah.
De Sitter.
De Sitter. Oh, De Sitter cannot be supersymmetric, so I will not be considering it. Unfortunately, yeah, it's I wish I could. All right.
Can be supersymmetric in the context of pseudo supergravity theory.
This talk will limit itself to type 2
Okay.
supergravity. But yeah, well, maybe I could say more, but I prefer actually getting back. So there is a modification also. There are some people who have tried to modify this formalism to break supersymmetry a little bit to allow for controlled supersymmetry breaking. And that maybe would also allow you to have the zeta solution within this formalism. So at the moment it's not covered. Now, however, you see I have this limitation 4 times 6, and also the 4-dimensional factor had Minkowski or ADS. That was it. This was the situation since 2005. Now, in this talk, I'm going to describe a solution to this problem, or to this limitation. Namely, I'm going to extend the formalism to just any supersymmetric solution. Actually, with those factorizations I showed you in the previous slide, or with no factorization at all, no ansatz necessary on the spacetime. So I will reformulate supersymmetry in terms of differential forms. And well, the rest of the talk, first I'll review a little better the system that I just showed you, the one that is valid for ADS4 or Minkowski 4 times an internal manifold. Then I'll show you the algebraic part of the new system. As I told you, you always have an algebraic part to this reformulation in terms of forms, and the differential part. And then at the end, I'll show you the differential equations. All right, so as I said, I'll limit myself to type 2. And by the way, so perhaps so I should say that so maybe I'm making it sound like I'm the only one who had the idea of reformulating supergravity in terms of differential forms. No, and many people have done so both in type 2 and also in any other supergravity theory. So this method is usable in any case. My claim, I would say, is one of generality, that I'm covering the most general situation in type 2.
Is there, could you impose an orientable projection?
It will be allowed. It is allowed. You can impose it. If you impose an orientable projection, then those forms, phi plus and phi minus, will have to transform in a certain way, which is known. And in fact, I did myself. I found solutions of that type, so it is doable. So, since we are in type 2 theories, and specifically, like I said, I like to focus actually on type 2b, just for convenience. We actually have two supersymmetric generators, epsilon 1 and 2, and we can decompose them using the factorization spacetime. In this first part of the talk, I'm going to review what happens when you do factorize spacetime, and later I'm going to waive this factorization. So if you do have this factorization, then you can factorize your spinors, and you find two internal spinors, eta 1 and eta 2. And now you can build forms the way I showed you before. So you can have bilinears. In this case, you can think, for example, all right, let me build, since I have two internal spinors, I can start building a bilinear eta 1 dagger, eta 2 with two legs, or maybe with 3, or with 1, or maybe I can have eta 1, eta 1, eta 2, eta 2. There's a bewildering array of possibilities, and it turns out that actually a more efficient method is to package them all into a single object. So what you do, instead of taking all these bilinears, you take the mother of the bilinears, which is this bispinor here. So this tensor product just means that I'm consider the product of two spinors, and that's an object with two free spinorial indices. So it's a bispinor. But now here's the basis, a convenient basis of bispinors. These gammas have also two free spinorial indices, and so I can think of them as bispinors, and I can translate any bispinor into a differential form this way by this dictionary. And this is called the Clifford map. In fact, we use it, for example, when we translate the Ramon-Ramon part of the spectrum. I mean, the Ramon-Ramon field originally, the way it comes out of the quantization of the string would be a bispinor, but then we quickly translate it into a form, and we treat it as such. And so I'm just doing the same now with also these guys. And their components along this basis are exactly the forms that I was considering before. And so these are actually what these are the 5 plus minuses that I was showing you before. This is just a definition. And so this, in the sense, they are just differential forms. But from other side, they start their life as bispinors. Now,
Excuse me, why do you always form? There's a one, eta 1.
Why eta 1, eta 2 on this?
Why not eta 1, eta 1?
I could, all right, very good. So I could have also applied the same logic to eta 1 dagger, eta 2 dagger. It turns out that if you compute the equations for these guys, for this 5 plus minus, eta 1, eta 2 dagger, so you compute them, then it turns out that those equations are already necessary and sufficient for the original supersymmetry equations to hold. You don't need to impose anything else on eta 1, eta 1 dagger. I don't know why that happens. I mean, or maybe, I mean, technically I do know, but I'm not sure I can give you. Anyway, so think of it this way. Of course, the derivatives of these guys contain both in their belly the derivatives of eta 1 and derivatives of eta 2. And the statement is that they don't mix them. I mean, they still contain all the information of those derivatives in the end. So now we face a similar question to the one we had in the introduction. Now I give you a pair of forms. If I want to reformulate the supersymmetry in terms of these forms, I should know when they have fermions, when they can re-express as bilinears or fermions, bispinors in this way. It will not always be true for any pair of differential forms of opposite degree, of even and odd degree, 5 plus and minus. And that's where the algebraic constraints will come from. So the answer to this question is easiest if you introduce the generalized Lorentz group, which I would define this way. Instead of just having the usual ordinary rotations as generators, which would be for SO6, you also add, so here the generators would have one index up, one down, and here in this generalized Lorentz group, there are also generators with both indices down, both indices up. And then the answer to this question turns out to be that you have to look at the criterion is the following. You look at the stabilizer of both of them in this group, so the leader group, if you want, and that needs to be SU3 times SU3.
Why do I introduce this generalized? I mean,
it turns out that the answer to this question is easiest in this form. But maybe I can try to give you a sense of why.
Yeah. That's right.
But I'm afraid I'm going to fail. But let me try. So
Could you remind us what the question was?
the question is the one up here. So when you have two forms, one odd form and one even form, and you ask yourself, can they be written in this way? Eta 1 plus, eta 2 plus dagger, eta 1 plus, eta 2 plus, minus dagger. And the answer turns out to be this. Now, why he's asking why? I mean, this one seems like it has dropped from the sky. But the thing is, if you think of this as a bispinor, it's already clear. So it has two copies of the Clifford, of the ordinary Clifford algebra that act on it. The copy that acts on the left and the copy that acts on the right. So you can think of it. You can think like there are already two independent copies of SO6 that act on it. Or rather, yeah, so if you have these two Clifford algebras that act on from the left and from the right, that actually the product of these two is isomorphic to a new Clifford algebra that has to do with this generalized Lorentz group, or the Clifford algebra of the double space, if you want, Clifford 6,6. So Clifford 6,6 is isomorphic to two copies of Clifford 6 which act from the two sides. And actually that has to do with why this is the correct answer. So each of the etas has this little group, SU3. That's just true in 6 dimensions for any non-zero fermion. So if you are imposing that the little group of these two is two copies of SU3, then you are kind of guaranteed, I mean, each copy of the SU3 will come from the little group of one of the two spinors. That's more or less why.
Sorry, what's the definition of phi being pure? What's the precise definition?
Oh, which one, sorry? Pure?
Phi is pure, yeah.
Yeah, so you notice the pause. So that's because I just wanted to say that there is a definition that follows from this fact. Purity is just a statement that this one viewed as a spinor, so in something which is acted upon by this doubled Clifford algebra, has an annihilator which has dimension 6, which is you might say, well, where does this definition come from? Well, the space of spinors is divided into several orbits, and this is somehow the smallest, and so it's pure because it's just like you're mining for something and then you find something pure.
So if you decompose this pi spinor in terms of forms, it's the one form vanishes basically. Is that what happens?
There is a reformulation. Now you would have to do bilinears in terms of these guys, and you can reformulate it. I believe you can reformulate what I just said in terms of. I know what you're thinking about. It's you have in mind the constraint that you impose in 10 dimensions. It might be that you for spinor to be ordinary spinor to be pure. I believe that it's more than just the one form that you have to set to 0. The bilinear, anyway. We better discuss it later because I'm getting.
Can you remind also what is the eta 2 plus minus? The plus minus
to chirality, just the chirality of this.
So we project plus and minus.
Yeah. So spinor.
6 chirality.
This is so 6 chirality. All right. Now, this is the statement. Somehow, phi plus minus contain all of the information of the etas, and that shouldn't surprise you from the previous slide. But also, they have all the degrees of freedom. From a phi plus minus, it turns out you can also determine a metric, a B field, and a function that you can call a dilaton if you like. So
your plus and minus are chirality, odd, even.
For the forms, they are odd, even. For the spinors, they are
So this G and B field and phi is for the even forms, right? For the odd ones.
Sorry.
For the odd forms, you get something else. You get the omega and
Yes.
maybe a one form.
Yes. Phi minus would have a 1 form, a 3 form, and 5 form inside, and phi plus would have a 0, 2, 4. But this B, I'm not saying that this B is the 2 form inside phi plus. It's more involved, but it does have all. These phi plus and minus do have all the. Like I said, these have some non-trivial algebraic constraints, which is what I wrote. I mean, that fact that they have that certainly the group, and then the general solution has been found, and it has been found that once you count the degrees of freedom in that general solution, it has whatever the correct dimension, 55, I don't remember, for all the degrees of freedom here. And there is actually a way. I mean, there's more than that. There's just a way of given these two guys to get all these degrees of freedom. It's not trivial. I'm not saying I just proved it.
You take some inner product of these guys or something.
Yeah, basically. Now, the differential equations are the ones that I showed you before, but also this time I'm also reminding you that there is this algebraic constraint. So once again, algebraic constraints and then differential constraints, which are the ones that I showed you before. Now, well, I introduced an extra element, which is that if you also have the Neuer-Schwarz free form, then it gives a contribution. It just changes d, the usual STO differential, to this d minus h wedge. This is weird, you might think, because this goes up 1 form degree and this goes up 3, but that jives well with the previous remark that these are forms, formal sum of forms with different degrees, and so there's no reason that the two pieces here should go up the same amount. Now we get to 10 dimensions. So this is now the new stuff. That was old stuff. Factorization. Now we forget about factorization. That's what I want to do today.
That's a quick question before you do that.
Yes.
Normally the SO66 generalized geometry is somehow associated to T-duality.
Ah.
I mean, a coincidence, or have you got anything to say?
There's one, for one thing, let's say, within this formalism, T-duality appears to be particularly natural. Okay. That's the safest thing I can say, but also maybe the least informative. Now, in my opinion, so there are these two, I would say this is generalized complex geometry, where the generalized goes together with complex. I mean, it's the complex that gets generalized, not the geometry. And then there is, of course, also this topic of generalized geometry, where generalized goes to geometry, not to complex. There's no complex either. But, and the two seem very related, and there's this SODD here that somehow seems to be doing something. Maybe this is telling us that one day we'll be able to put them together and to have these few spinors also for the situations like the ones you are considering. Especially because, I mean, it does seem tailored.
Isn't it obvious if you have one compact filters? I mean, one supersymmetry comes from the left movers, the other from the right movers, and obviously you have independent SO6.
Yes, but
so I was going to ask whether you can, the 2,0 vacua are also described by this, but since you don't use world C.
Yes, morally, but I think I believe he was asking whether, because this SODD mixes, say, momentum and winding modes, but here I'm not doing that, right? I'm not.
Well, you don't know at the level of this discussion, you don't know, but the 2 SO6s act on left and right movers the way you wrote. If you have one vacuum.
That's right, but I'm not using this SODD symmetry to mix in a strange way the the space-time and some dual space-time, which is what I mean. At least this is the way I was reading his question, because I know what he does.
Here you typically don't even have winding modes, right? If you have a Calabi or simply connected, then there are no winding.
Yeah, for example, from other side, some other people might tell you, oh, even the Calabias are torus vibrations, so maybe you could do something to the torus vibration. Yeah.
It would be curious if the generalized geometry that was made complex was the same as generalized complex geometry. But your point's obvious.
Well, I don't know. I think the action of the SO66 is exactly the same.
It's the same.
The action of.
It's the same.
It is. I'm just saying that I'm not also acting somehow on the coordinates. and not messing with the geometry.
So you mean the Bush rules are not
Yeah, not exactly. I'm not transforming anything under T-duality here. It says if everything is ready to be transformed under
You're just saying
T-duality,
there's a
everything is assembled in a way which potentially makes it very.
We can discuss it afterwards. I think the Bush rules are and they don't mix wine because you are assuming locally constant.
But I mean, they're in there, but they have to do something to the phi's, for example. When I perform the Bush rules, I'll do something to the fields.
Yes.
And then simultaneously, I will have to do something to the phi's, which is something pleasant looking, but I'm not necessarily doing it. And I think, so in many situations, you might want to say, oh, now I have transition functions valued in ODD. And that's a very attractive thought, but I'm not actually using that possibility. I'm being conservative, even though it might not look so. So, well, all right, let's get back to what I was saying. So I reviewed this, what the system looks like for the factorized case, 4, 10, 6. Now we want to see what happens in 10 dimensions. Now, the first question is the same as the one we had earlier. So remember, when we built a bilinear, and then we were trying to see when that bilinear came from spinors, and it was essential at some point I needed to know what the little group of a spinor in 6 dimensions was, and I told you it was SU3. And now, well, as a preparation, let me remind ourselves what the little group of a 10-dimensional spinor is, because that will be kind of crucial. So first of all, let me once again build a bilinear. This is a bilinear with only one leg. Since we are in Lorentzian signature, it turns out that this guy is always light-like, this vector here. And now let's see. What I want to do is actually what I want to compute is the little group of the spinor. But as a first step, just to make the answer more intuitive, let me compute the little group of a light vector of k that I have constructed from epsilon. This is the light cone, and the Lorentz group acts on the light cone, clearly. I mean, it keeps it invariant. But then, imagine cutting the light cone with a plane. You get time equals constant, or zeroth component equals constant. You get a sphere. In 10 dimensions, it would be a S8, 8-dimensional sphere. And that's called usually celestial sphere, because it's really what you see. Because these are all the possible directions of light rays. Now, one more step behind. Let me solve the same. Let me ask the same question in 4 dimensions. What is the little group of a light vector in 4 dimensions? Well, maybe all of you remember the answer, but let me do it this way. So in that case, the celestial sphere is an S2, and well, the Lorentz group is SL2C. It's isomorphic to SL2C. And how does the Lorentz group act on the celestial sphere? Well, the answer is cute. It's via Möbius transformations, which are these. I mean, if you put A, B, C, D in a matrix, that matrix will need to be in SL2C. Now, if you want a little group, choose a point, and choose, for example, the point at infinity, and ask yourself, what is the subgroup of this SL2C, which keeps the point at infinity invariant? And that's just translations and rotations, AZ plus V. That's it. And this is the Euclidean group. It's the group which has rotations in 2 dimensions and also translations. I could have given this answer straight out. After all, we probably have We should all remember it from the books in quantum field theory, which use this in the context of looking at the unitary representations of the Poincare group in the case of a light-like momentum. But it's fun to rederive it. And in general, turns out the answer is this. You get, again, this roto translation loop, which otherwise might look a little strange, so that's why I rederived it. So for us, in particular, it will be SO8, semi-direct product R8. This is the leader group of K. Now, I'm not actually interested in K itself. Now let's get a step back. So the parenthesis has disappeared, let me go back to epsilon. Well, it turns out that epsilon, so if you build the bispino, so the bispino is made up of all the possible forms that you can build by doing bilinears. The bilinears, remember, with many possible legs. And it turns out that in 10 dimensions, for various reasons, this K can only be 1, 5, or 9. And the 1 is just a vector we have discussed before. And this guy, the 9, is just the star of the 1 part. And this 5 form, now what does it do? Well, let's see. If you have a light vector, now the space which is orthogonal to the light vector is 9-dimensional, but of course it is also tangent to K because K is light-like, so it belongs to its own normal space. So now I can actually say, all right, out of this 9, I'm not interested in this one, so let me quotient it away. Let me consider a slice which doesn't contain it. And this is 8-dimensional. And in that 8-dimensional space, you can consider this form. So you can contract K with the 5 form. You get a 4 form. And now a 4 form in 8 dimension defines a spin 7 structure. If, not any 4 form, it should be a 4 form with certain algebraic features, but you can prove that those algebraic features do follow from the definition. So this makes it, this breaks SO8 to spin 7, and this is our answer now. This is the stabilizer of the epsilon, this little group of epsilon. And so I'll be calling it inhomogeneous spin 7, just the same way as this is usually called inhomogeneous SO, ESO, and this is I-spin. Now, when you have 2 spinos, once again, so you can define many bilinears. I could, getting back to his question, I could have now defined epsilon 1 bar, epsilon 2 bar, but because of the experience with the factorized case, I decided to just have a look at this guy. So this time it's a single form. The plus or minus is no longer an option, because if you choose a theory, you have already chosen the chirality of both epsilon 1 and epsilon 2. And now you ask yourself the same question. When can a form be written as a bispino? When can it be translated into a bispino? When does it have 2 spinos in its belly? And once again, the answer turns out to be simple in terms of, simple-ish, in terms of this generalized Lorentz group. And, well, because of what we saw in the factorized case, maybe we would expect that the stabilizer should be made up of just the stabilizer of epsilon 1 and the stabilizer of epsilon 2. But that is actually not the case. The right answer is that the stabilizer should be this huge group here. Now, actually, last week I was talking to Pierre Van Hove, who showed me that very similar expressions appear in the context of the talk he gave us. So this is not actually, once put in the right context, this is not actually that unreasonable. But all you need to know about it actually is the following. First of all, phi is no longer a pure spinor, so that feature of the factorized case is not kept. And so that's actually part of the reason I didn't insist on that definition.
Sorry, may I interrupt you with a very, very basic question?
Those are the best.
I'm not really, to me it's not really clear what you're trying to solve. Are you trying to reformulate type 2b supergravity into a form of spinors or what?
In terms of forms, in terms of that form. But if I really want to reformulate it, I want to make sure that phi has inside it the data of two spinors, that it can determine two spinors. And then those two spinors will hopefully satisfy the right differential equations that they should in order for supersymmetry to be preserved. Because if I just derive the equation for phi and then forget about the fact that phi comes from spinors, then I have not really reformulated. I want to be able to prove that I can go back. Once I write my equations, I want to be able to prove that I can go back. And this is what these algebraic constraints are for.
And the other question is about this generalized Lorentz symmetry. So something like SO1,9 acting on each spinor, or how do you get to this SO1,9?
That's related. That's what more or less what I was trying to say as an answer to his question. More or less, that's the origin of this generalized. You can think of it that way, because the action on a bispinor is made up of acting. There's a little. I lied a little bit. So you have infinitesimally, you have actions of. So infinitesimally, you know that the action on a spinor is made up of acting with two gamma matrices. Now, on a bispinor, you can act with two gamma matrices from the left, or two from the right, or one from the left and one from the right. And that's so all the possibilities, and you get a big matrix, and that's what I can show you more concretely. But actually, that's part of the reason why we get this ridiculously big group.
No,
and
I guess my question is just much more basic. When you talk about the SO6,6, it's not 6 time and 6 space dimensions. If you talk about SO1,9 as the Lorentz group, it's 1 time and.
You're wondering why I have this signature, why I have this mixed signature.
This in this SO10,10. What are?
I mean, the origin is the following. If you have one forms and vectors, there's an natural metric, which is just taking contraction between the two. And contraction between a vector and a vector gives 0, between one form and one form gives 0. And then you have identity and identity, because let's say dx1 and del 1 give 1 and so on. And in general, you have a delta, which is this identity here. So now this is a quadratic form which has signature d. It has as many pluses as minuses. If you try to analyze it, you see that this is mixed signature.
It's just like the ODD of the T duality.
It's just like the ODD of the T duality.
Are you treating the original 10 dimensions as Euclidean dimensions as against Lorentzian dimensions?
It would be this SO19 and SO91
still makes 10, right?
Yeah, inside. Yes.
And that's why your solution is more complicated than yours.
Yes. That's right.
Yes.
Yes. The signature is really crucial on this. So anyway, you don't need to. One message is that you don't need to remember that big stabilizer, because I actually was able, using it, to solve to find all the possible solutions of the constraint. So this part, I mean, basically the message here, the algebraic part of the equations is done. I mean, I have the solution, demonstrated the solution. Practically, there's nothing left to do. However, one difference one lesson is, unfortunately, phi does not determine a metric by itself. And by lying a little bit, I can tell you more or less why. Well, I told you that, well, now for some reason I called it K1 because there are now two spinors, epsilon 1 and epsilon 2. Let's pick epsilon 1, let's define K1 from it. This is a null vector, as we said. And then there are, a null vector also defines a orthogonal space, which is 9-dimensional, but it contains also K. So basically, there's nothing being said about the other, there's nothing, epsilon 1 that only says stuff about 9 out of 10 directions. And there's one direction that will never appear in any bilinears, basically. And what happens is that if you try to write equations merely in terms of phi, there will always be some components of the supersymmetric equations which have to do with this missing direction here, which are not reproduced. So that's the message. Having said this, now let me show you finally the differential equations. Well, like I said, there are two like vectors, which are K1 and K2 associated to the two spinors. Let me form semi-sum and semi-difference. And in terms of this, there are two old equations. Old meaning that someone else had found them before me, damn it. And they're pretty nice. Actually, one says that this sum here is always a Killing vector. The other says that, well, this, you might say, what does it mean? Well, it does imply that H is also kept left invariant by the action, by the Lie derivative of K. These two actually also appear in other contexts, such as when gauging a sigma model. So they appear to be.
What is K tilde?
K tilde. Oh, it was supposed to be this.
Ah,
I really forgot the tilde. Okay, sorry. This is K tilde. Yeah, these two equations are the way I said. K equals this and K tilde equals this. Sorry, my bad. Yeah, this is these two are. You might say, oh, but this is. You told that these are vectors. Raise and lower the indices as needed. This is more naturally a one form, and this is more naturally a vector. This is now a contraction of a vector with a 3 form that gives you 2 form, and this.
Okay. Is there a difference here between type 2A and 2B?
Not in this.
I mean,
not so far.
Time-like. Yeah. In type 2B, I see that K is time-like. In type 2A, maybe.
No, these two K. Oh, I see. These two are both light-like, but the sum can be like when they're parallel, or otherwise will be within the like form, so time-like. Anyway, since my time is up, let me show you the equations and then I can conclude. What about phi? Well, this is the equation that I got for phi, and I was pretty satisfied by this. First of all, because it's pretty compact, and in my opinion, even maybe elegant, and also because it reproduces the equations we had before when restricted to the factorized case. You get basically the system we had before now with a couple of steps. So at this point you might have thought, okay, so maybe this is the system that will be equivalent to supersymmetry, and that would have made me ecstatic, and that for some point I believed it. But however, we know from our previous discussion that phi does not really have all the data inside it. So there was that discussion a couple of slides ago where I told you it doesn't really have all the data for to determine a metric, for example. So it's suspicious. Will this be equivalent to supersymmetry? Well, no. This turns out to be the answer. You have to add 2 more equations. Now, the good part is that here, no ansatz is necessary. This you can apply to any 10-dimensional supersymmetric solution, even with one supercharge if you like, any spacetime factorized any way you like or not factorized at all. So it's good because it's general. It's also good because it's basically the same system into A into B. So what changes, as an answer for the answer to your question, what changes is what phi will be. So the concrete solution to the algebraic constraints actually differs a little bit from to A and to B. And I have all the possibilities written down in the paper. But otherwise, the system looks the same. Another good thing is that there are no covariant derivatives. Here I have again the same dH, which is very natural for differential forms. And I don't have to compute any Levi-Civita. But the bad thing is probably what you were wondering about, what the hell is this doing here? Because it looks like I'm mixing the spinorial and form picture. Well, this is a mix of a wedge and of a contraction. And it makes these equations slightly, quite a bit more complicated to handle than this one. And finally, I have this appearance of these directions that I told you before that are sticking out of the 9, which have to do with the epsilon. So these are not E plus, this E plus 1 and E plus 2 are two data, two extra data that supplement phi in order for it to have all the degrees of freedom to determine a metric. And, well, that's it. So we saw that supersymmetry in type 2 string theory can be expressed in terms of forms. And this is, in my opinion, a little better conceptually than the system for the factorized case, because the system for the factorized case is maybe good practically and maybe it's telling us something about the geometry of compactifications, but it cannot have anything to, by itself it cannot say anything fundamental about some, I don't know, reformulation of type 2 supergravity, because it was only, as it was only limited to the factorized case, not to just to any geometry. And well, there are still some features of the generalized geometry, generalized complex geometry, but the language is significantly different from the one that Hitchin introduced. Thank you.
Questions?
Probably a trivial one, but where is the number of supersymmetries visible in this number of components?
Yeah, at some point I said that even one supercharge is allowed. So each solution to this will be one supercharge. So then you can find if you find a modular space of solutions, for example, many solutions, and usually they will have to form a certain space, then that will be and n equals something. That will correspond to having more than one supercharge. The same is actually true for the for the factorized case. In the factorized case, each solution of the system I showed corresponds to having n equals 1. And then if you want to have n equals 2, you need to have a family of solutions. And the basis of, so here's the
Since you look at supersymmetric solutions, I guess you can leave time alone. Would it change anything if you had SO99, I suppose?
Yeah, so I can leave time alone, but You're saying that because you expect that things will be stable in time if there is supersymmetry.
Yeah, well, the Hamiltonian is part of that.
Well, here you actually do see that because this K is actually the symmetry that. So you can see actually explicitly that each supersymmetric solution will have one, at least one isometry, which is a K. In fact, you can also show with this formalism with 2 lines. You can show something that other people had said a few years ago, which is that actually leaves everything invariant, not just the metric, but all the forms. Now, in the case of where that K is time-like, then in a sense I can leave time alone. And there was a paper by Kerber and Martucci where they had looked at this factorized 1 times 9. They initially had looked at that setup actually, but then after a while I convinced myself that this was going to be a little more practical. It didn't seem to offer, leaving time alone actually didn't seem to get rid of the problem I was telling you about. The extra equations will still be there, for example.
The killing vector can be like.
I think so. I don't know if I can come up with maybe some PP wave solution or something that might have that K like. But anyway, even if you said, all right, that's a very strange case, let's leave it alone. Even if you said that, I convinced myself that I wasn't gaining too much by having a factorized, and that's why I eventually worked. Oh yeah.
So the supergravity, presumably here you're thinking in a sort of democratic formalism where you've got forms in their joules. So does that mean you're including the massive 2A as well in this story? Is the massive supergravity included in your?
Yeah. I'm a bit confused because so first of all, as an answer, I was starting by answering that first of all, I haven't said it, but this F, yes, is the sum of everything, and it's self-dual in particular. But then I'm confused. So why are you pointing at the massive case in particular?
Okay.
It would just be.
It could have an F0 in it.
Yeah, it's just it is allowed to have an F0 here. Because after all, there's no contradiction if that's what they were thinking, because even though this will never have a 0 form, I mean the 0 form here might just be killed by these guys.
So I got a question and a conjecture.
Okay.
So if you're going to do 11-dimensional supergravity, then you might want to try and do the same tricks. So I'm going to predict that you won't need SO groups because that's not what naturally comes out of 11 dimensions, but the generalized geometry that comes out of that is more to do with the exceptional groups. So you need spinnerets for the exceptional
And
groups.
now you're on the record.
That's fine. Yeah, I'll stand by that.
This is a natural outcome of our discussion the other day. There's also there are also those papers by Dan Waldron and others where they have something similar for the factorized 4+7 case in M theory. On the other hand, you were telling me that you were not satisfied by that.
No, I'm satisfied.
Okay.
No, I absolutely.
I was trying to push into compromise himself.
I'm completely satisfied by them. I mean, I think it's that they have the same thing we got just with this section condition, and then you're using the section condition because you're just using the generalized geometry on the tangent space, so it's completely consistent. So it's just a case of when you're doing the M theory version, it's more the exceptional groups which come out of U duality, and then you need the sort of spinner rep of the exceptional group, whatever that means.
What do you mean by that?
Yeah, exactly. So I would know what I meant if it was, for example, when I say exceptional groups, I mean the series of them, which would begin with. You could even have SO55, only it'd be the 16 of SO55. Or I could have, I mean, I think there's some notion of what you mean by the spinner rep of some exceptional group. If Bernoulli was here, he would tell them. Sure.
But normally we consider spinner some representation of the compact subgroup.
Yeah, something like that. Not
which
really.
is well known.
Right.
I should mention just something just for the supersymmetric solutions in M theory have been looked at from the point of view by linears by Jérôme Gontet
Sure,
and Pakis very
Yeah, I
long
remember
ago, and that might actually be a starting point for an investigation. I mean, that was before this generalized.
Yeah, they had all this
geometry
K
business.
stuff there, and then they had restrictions on
Yeah,
K.
so
and stuff like
yeah,
that.
I think we should also mention that
Yeah, I mean,
might be related to whatever one wants to.
Especially when it's on the record.
Everything is so official here that
Don't worry.
Everything is on the record now.
Any more questions? Or we can go off the record with some wine in a minute. Okay, let's thank the speaker again.